Hello again. We're going to continue our discussion of differential equations. Now that we've talked about how to set them up, we're going to talk about different strategies to solve those differential equations. The first strategy is going to be to separate the variables. So let's get started. The first thing we're going to do when we are trying to separate the variables is to try and get all x values on one side and all y values on the other side by using multiplication or division. Okay, and then when we see dy dx, we're going to split it as if it were a fraction. So we're going to put the y and dy all on the same side and x and dx all on the other side of that equation. So when I do that, I'll be able to integrate both sides. One side will have y's with a dy, the other side will have x's with a dx, and I'll be able to integrate both sides separately. So here's an example. I have dy dx equals the cosine of x times y plus 3. And you'll notice that I've got x's and y's together on one side, and I've got dy's and dx's together on the other side, and I want to fix that. So what I do is I divide both sides by y plus 3, and I multiply both sides by dx. And what that's going to do is it's going to give me 1 over y plus 3 dy on one side and cosine of x dx on the other side. So as you can see, I now have my y's and dy's all on the left, and I have my x's and dx's all on the right. Now I'm ready to integrate both sides. Luckily, it's not a difficult task to integrate either one of those functions. The left side just becomes natural log of the absolute value of y plus 3, and the right side just becomes sine of x plus c. Now you'll notice I only put a constant on one side of the equation. Technically there are constants on both sides, but if I collect them on one side of the equation, it makes my job much easier to do. And I'm allowed to do that algebraically. All right, so now I'm solving for y, so I need to get rid of that natural log on the left, which means I will raise both sides as an exponent of e, and I get y plus 3 on the left, and I get e to the sine x plus c on the right. Now, knowing my properties of exponentials, I know that I can split the e to the sine x plus c into e to the sine x times e to the c. Now, e is a constant and c is a constant that I don't know yet, so that whole e to the c thing, that is just one big constant. So that's how I'm going to write it. I'm going to write it as just a capital A. That's going to represent e to the c. It's a lot easier to solve for one constant than solving for a constant that's being raised to another constant. It's just unnecessary work. Then solving, I get that y ends up being a times e to the sine x minus 3. All right. Now here's another example. I have cosine squared of x dy dx equals e to the negative y. X is going from 0 to almost pi over 2, and I have a boundary condition this time that x equals pi over 4 and y equals a half. So I'm going to have to solve that. Once I get a constant, I'm going to have to figure out what that constant is. So I take the original equation, and to get my y's on the left and my x's on the right, I'm going to have to divide both sides by e to the negative y, and I'm going to have to divide both sides by cosine squared x so that I get that equation there, and also I have to multiply both sides by dx to get that dx to go over on the right-hand side. So now I have all y's and dy's on the left, I have all x's and dx's on the right, and I'm ready to simplify it first. So 1 over e to the negative y, that can be written a lot more simply as e to the y. 1 over cosine squared, I can write that as secant squared. And now I'm ready to integrate both sides. The antiderivative of e to the y is just e to the y, and the antiderivative of secant squared is just tangent x. And again, I do have constants on both sides, technically, of that equal sign, but I'm just going to collect them on the right-hand side of that equal sign, so I only have to solve for one thing. Now I'm going to plug in the x and the y that I was given. Pi over 4 is my x, and 1/2 is my y. So if I plug those in, I get e to the 1/2 equals the tangent of pi over 4 plus c. So I'm just solving for what c is equal to, so I can finish writing the equation, the specific equation for this example. So e to the 1/2 equals 1, which is the tangent of pi over 4, plus c. So my constant is going to be e to the 1/2 minus 1. All right, so e to the y equals the tangent of x plus e to the 1/2 minus 1. But remember, I'm solving for y, not e to the y. So I've got more work to do. y is going to equal the natural log of the absolute value of tangent x plus e to the 1/2 minus 1. All right, so that is how we solve differential equations by separating the variables. If you have any questions about that, please let me know, and I will see you tomorrow.